In this video we look at symmetry of graphs around the x-axis, the y-axis, and the origin. Sometimes you say symmetry with respect to the x-axis, y-axis, or origin. Let's begin with symmetry with respect to the x-axis. Graphically, what this means when you have symmetry with respect to the x-axis is every point has a mirror image across the x-axis. Okay, so here's an example of a graph. This graph is symmetric with respect to the x-axis. Imagine each point, this point here, has a mirror image across the x-axis down here. And every point on the graph has a mirror image across the x-axis. So this graph is symmetric with respect to the x-axis. Now, what does it mean algebraically to be symmetric with respect to the x-axis? Well, what it means is, take an ordered pair like this guy right here, and let's say this is x and then this up here is y. So this ordered pair on the top would be the ordered pair x comma y. Then what would the ordered pair for its symmetric counterpart be, its mirror image? Well, the y would be negative y. So the ordered pair would be x comma negative y. And that's precisely what tells us the algebra of symmetry with respect to the x-axis. In an algebraic equation, if we replace y with negative y, we get an equivalent equation. Okay? If we replace y with negative y, we get an equivalent equation. You can see when you have symmetry about the x-axis, y and negative y are symmetric counterparts. So let's see some examples of this. Let's consider the equation 2x minus 5 equals 3y. And what I want to do is replace y with negative y. I don't do anything to x. So now I've got 3 times negative y. So the question is, will this be equivalent to the original equation? Okay, so let's come over here actually and do this. So I've got 2x minus 5 equals 3 times negative y is negative 3y. And just so I can compare them clearly, I want 3y to be on the right side of this equation also, and then I'll see if they are equivalent. So what I'll do is divide both sides by negative 1 to make this positive 3y on the right. When I do that, I get negative 2x plus 5 on the left, and these two equations, the original and this new one, are not equivalent. So this equation, so 2x minus 5 equals 3y, is not symmetric about the x-axis. So you can see there's lots of ways to say that symmetric about the x-axis, symmetric around the x-axis, symmetric with respect to the x-axis. But you can see in this equation it's not symmetric about the x-axis. Let's try another one. 2y squared equals 5x squared plus 12, and let's replace y with negative y. When I square negative y, I get y squared because this negative becomes positive. And I can see that this equation is equivalent to my original. So this is symmetric. 2y squared equals 5x squared plus 12 is symmetric about the x-axis. Okay? Alright, so that's the x-axis. Let's look at the y-axis. When we look at symmetry with respect to the y-axis on a graph, each point has a mirror image across the y-axis. So let's see an example. This graph, pick any point, such as this point down here maybe, and you can see as you go across the y-axis it has a mirror image point over here. This point has a mirror image point over here, etc., etc. So algebraically, what does this mean? If we replace, you can probably imagine, look at this ordered pair right here. Let's say this is x and this is y. Then this point would be x comma y. And what would its symmetric point be? Well, negative x comma y. So now, when we look at symmetry about the y-axis, if we replace x with negative x, we get an equivalent equation. Okay, so let's see some examples of that. Let's consider the equation y equals the absolute value of x plus 5, and I'm going to take a different equation where I replace x with negative x, so I've got y equals the absolute value of negative x plus 5. There's nothing I can do to simplify this. I can't do anything with this negative x because I've got the plus 5, so there's nothing I can simplify. These are not equivalent equations. So what that means is y equals the absolute value of x plus 5 is not symmetric about the y-axis. Let's look at another example. Y equals the absolute value of 2x. If I replace x with negative x, so I've got 2 times negative x, well, 2 times, sorry, I didn't mean to change colors there. 2 times negative x is negative 2x, and when I take the absolute value of negative 2x, that's the same thing as the absolute value of 2x, because multiplying by a negative does not matter when you take the absolute value. The difference in the previous example was addition. You can't simplify addition of inside absolute value, but you can simplify multiplication inside absolute value. And so what you can see is that these are equivalent. Thus, the equation y equals the absolute value of 2x is symmetric about the y-axis. Now, if you wanted to, in this previous example, you could factor the negative out inside, which would leave you with x minus 5. And now, since this is multiplication, you can drop the negative because the absolute value would get rid of the negative anyway. You'd have the absolute value of x minus 5. However, this is still not equivalent to the original equation. So the original equation is still not symmetric about the y-axis. Now let's take a look at symmetric about the origin. Every point in symmetry about the origin has a mirror image across the origin. Okay, so let's look at an example of a graph. In this graph, you pick any point, maybe this point here, and you go across the origin, which is right there. Then you get a symmetric point there. This point has a symmetric point across the origin over here. This point has a symmetric point over here across the origin. So when you go across the origin, you always go to the opposite quadrant and you pass through a straight line across the origin. Okay, so algebraically, what does this mean? Let's pick an ordered pair like this guy right here and say this is x and this is y. Then this ordered pair is x comma y. Well, what is the ordered pair for its symmetric point over here? Well, this would be negative x and this will be negative y. So when you deal with symmetry about the origin, x becomes negative x, and y becomes negative y. Okay? So, to test for symmetry with respect to the origin, when you have an equation, if we replace x with negative x and y with negative y, we get an equivalent equation. So let's see a couple examples of this. The first one, let's look at the equation x squared plus 4 equals 3y. So I'm going to replace x with negative x and y with negative y. When I square negative x, squaring the negative just gives me a positive, so I get x squared plus 4, and 3 times negative y is negative 3y. And like an example we did earlier, to see if these are equivalent, let's at least make the right sides match. So I need to change negative 3y to positive 3y, so I'll divide both sides by negative 1. So that gives me on the right positive 3y, and on the left negative x squared minus 4. And we can see now the right sides are the same, but the left sides are not, so these are not equivalent. So the original equation, x squared plus 4 equals 3y, is not symmetric about the origin. Okay, let's try another example to test for symmetry about the origin. Let's look at x times y equals 12. And I need to replace x with negative x, y with negative y, and see if it's equivalent. Well, negative x times negative y, since a negative times a negative is a positive, simply gives me xy equals 12, which is exactly the same equation. So they are equivalent, meaning that the original equation, xy equals 12, is symmetric about the origin. Now the tough thing about this concept is you could work with any kind of equation. So I've tried to work many different examples here, but it really comes down to understanding algebra and how to work with negatives. So if you run into trouble, certainly ask for help from your teacher or whomever you're working with. But the problems can vary quite widely because the equations can have just about anything you can imagine in them. Okay, but I hope this video was helpful. I hope you understand the graphs and the equations and how to test for symmetry.